So far in the course, we've been talking about single or scalar linear differential equations. Do we need to consider anything more? As a motivation, let's talk about what's called a parallel electric circuit. Now, in a parallel electric circuit, you take some sort of series circuit and then you add further loops to it. We've got a circuit drawn here where we've got a voltage source, and that voltage source supplies a current. I'm going to call this current I1, and that current has only one path to go. So it leaves the voltage source and it goes through this first resistor R1. And then it comes to this first, what we call junction or node, and then it has a decision to make. Should it go down and go through this inductor, or should it continue on this way and go through another resistor? The current splits to follow the path of least resistance. So we have a current that splits and then rejoins again at the next node to become that I1. So we've got two loops, two series loops that are combined. And there are some rules that you learn about in physics that will tell you how to set up a system that describes this. The node tells us that what goes in must come out. So current 1 must equal 2 plus 3. This first loop that I've labeled in purple, this loop follows the standard Kirchhoff's voltage laws. So the battery V supplies a voltage. The voltage drops a bit across the first resistor, so R1, I1. The part that goes through the next inductor branch, the voltage loss there is L1, L1 I2 prime. It comes back as I1 L2 prime. So that's what the first purple loop gives us. Now in the second loop, if you follow the normal rules, you will have no voltage source, so there's a 0 there. You could go across, let's say follow I3. You would lose voltage across the second resistor, so you'd have R2 I3. But because you're going in the opposite direction in the other one, you would gain it across L1 I2 prime. Now our goal here would be to say, what are all of these currents? What we're going to be able to do is rewrite this. So for example, from the node equation, I can replace this thing here. So this second equation would become 0 is L1 I2 prime minus R2 into I1 minus I2. In the first equation, I've got this L1 I2 prime and I've got this L1 I2 prime. So the first equation can also be rewritten V R1 I1 subtract negative R2 I1 minus I2 minus L2 I1 prime is 0. We're going to have a system of two equations here. From the reformulated equation 1, L2 I1 prime negative R1 I1, negative R2 I1, positive R2 I2, plus V. And from this reformulated second equation, L1 I2 prime, R2 I1 subtract R2 I2. So we're going to take everything in equation 1 and divide it by L2. So we'll have a negative R1 plus R2 over L2 times I1. And R2 over L2 times I2, and then a V over L2. So that's what the new equation 1 is going to give us. And then the new equation 2 is going to be I2 prime is R2 over L1 I1 subtract R2 over L2 I2. And just to make things explicit, I'll put a 0 here. This looks like a horrible mess. But note, what we've got here are two first-order DEs, because if you take a look at these sides, I've got an I1 prime and an I2 prime. There's a special structure. If you look at the I1s and the I2s, they are not appearing to any other power other than the first. Everything here is a linear DE. Because of this, we can end up using some matrix and vector notation. But what we need to do is define a matrix function and then a vector function. And why would we need to do that? Because remember that I1 and I2 are functions. So let's take the vector I of t and say that it's comprised of these two components, I1 and I2. If the I1 and I2 are differentiable, then what I can do is define the vector I prime as just the derivative of all those individual components. Now, the other thing that we can define a matrix function. So this could be what we'll say is a matrix of functions. you could have as many components as you'd like. Now I'm going to restrict it to be an n by n, because most of our theoretical results are going to rely on things being square, and in practice we often end up with square systems anyways. From linear algebra, we've got something called a matrix vector product, and this is a very important conceptual idea. If we were to have a matrix and it has a bunch of columns, so let's say A1, A2, and we go all the way down to AN, and we have a vector with a bunch of components, as long as the number of columns matches the number of components, we are going to be able to write it like this. The first component weights the first vector, adds to the second component weighted by the second vector, all the way down to the last one. Our system is going to be able to be written as I1 prime, I2 prime. We're going to put those into a vector. We are going to be able to write our system as a matrix times a vector. R2 over L2, R2 over L1, that was a negative, and R2 over L2. Sorry, that was a positive, that was a negative. This is going to be multiplied by I1 and I2, which are both functions. And then we had an extra term, a V over L2. It's a system of first order linear DEs. And we're going to write it in this suggestive form. It's going to be vector I prime of t. We're going to call this matrix here, P of t. Matrix P of t times vector I of t plus some function f of t. And it's a vector function. This looks an awful lot like a first order linear equation, right? When we had y prime of t, we could move over this other term, p of t, y plus f of t. In general, when we talk about this first order system, we're going to use the letter x. It's going to be a first order vector system. If this vector f is the zero vector, this is what we call a homogeneous system. Now, in a homogeneous system, you could write it as x prime of t vector is p of t times this x of t. And clearly, if the vector f is non-zero, it's a non-homogeneous system. We will also talk about initial value problems for first order linear systems. So for example, in our current problem, we might have the initial current at time 0 is 0, and the initial current for 2 also being 0. So we could have a vector of initial conditions. I vector at time 0 is the 0 vector. So this would be our vector of initial conditions. We're not going to prove it, but as before, there's a uniqueness theorem for initial value problems in linear systems. If I give you some initial value problem formulated as a linear system, x of t here plus some function, and we have appropriate initial conditions, so we'll call this a vector of constants. If these functions p and f are continuous on some interval a, b, and our initial value lives somewhere on that a, b, then there is a unique, so one single solution to this initial value problem. And that's really the foundation for what we are going to develop in terms of the theory. Now, for example, we could give you a homogeneous system where the matrix is made up of constants. So typically when the matrix is made up of constants, we just call it a matrix A. And so our system here would be x prime equals ax. If I give you this vector, this is a vector of functions. So let's say e to the 5t, e to the 5t. We would write this as e to the 5t 1, 1. Is x1 a solution? Okay, well, x1 prime of t would be like saying take the derivative of each component, and that would give you 5 e to the 5t, 5 e to the 5t. And if you wanted to, you could write it as 5 e to the 5t into 1, 1. So we're going to sub this into the DE and see if it actually satisfies the equation. So we'll have 3, 2, 4, 1. And now what we're trying to do is a matrix vector product, e to the 5t, 1, 1. Now this is a constant. And because it's a constant, we can use linearity of matrix vector products. And that can get pulled out And what we'll have is e to the 5t is a weight in the front, 5, 5. That is equal to 5e to the 5t, 1, 1. And that's exactly equal to x1 prime. x1 solves the dE. But if I give you this x2, where I'm e to the negative t, negative 1, 2, this also solves the dE. So we've formulated a dE. I've verified that certain functions, vector functions, can solve the dE, but now it looks like I have two. How many solutions are there? And that's what we'll talk about in the next video.